Hey folks, welcome to the next episode on Clear My Paper. Today we are going to cover determinant of a 2 by 2 matrix. I'm going to put a series of videos on determinant itself to cover the syllabus. Some of them will be from an exam standpoint of view, which will be like a Clear My Paper on theme, and some of them will be like a clear your head, where you need to have some intuition on why certain things are happening and stuff like that. And typically, whenever I put something on the intuition or try to just address your curiosity, textbooks usually miss that. Textbooks just stick to the point and they start from a middle of somewhere where students have no perspective of why that formula came from, where did that came from, and that's what I'm trying to cover in this set of videos. Okay. So, like I said, this is going to be a clear your head or clear my head episode. You got to watch this if you are going to be curious. You need to get to the bottom of things. You are interested in grounds of learning, or you want to just have some intuition on the whats and the whys before you get to the house. And if you belong to that kind of a mentality, you should watch these videos. If you're just focused on getting the exam marks, or you don't have time, or you just don't have the bandwidth, and your focus is going to be clear my paper, then you can just skip this videos and the next set of videos and just focus on the videos which are relevant for your exam standpoint of view. Okay, let's take a deep dive on determinant of a 2 by 2 matrix. Okay. All right. So, like in other videos on determinants that you'll see, or in matrices generally, we'll always switch back between the algebraic side of the matrix or this chapter and the geometric side. Today we're going to talk about determinants. So again, we'll draw parallels between the algebra and the geometry. This video for today or this episode is completely on the algebraic side of it, focused on the 2 by 2 matrix. Okay. And similarly, you will have examples on 3 by 3 and other things coming up. So let's take a simple case of solving one equation and one unknown. If you remember, the whole matrices and the determinants kind of originated because someone back in the ancient century, 4,000 years ago, was trying to solve a set of linear equations, right? That's what we discussed in my opening episode, right? And eventually there was a journey all the way through the 18th century, and then matrix, determinants, linear algebra become a subject by itself, and rest we all know what was happening. So let's go back to the same example of solving one equation, one unknown kind of a problem in one dimension, like similar to our geometry, where we just take one example and then we move to the second dimension. Okay. So what does it mean, one equation, one unknown, right? So for example, I've just taken a simple example. Let's say we have a given equation where 5x is equal to 15. Okay. And we're trying to solve for x. So our objective is to find x, and we do a simple divide both the sides by 5 in this case. So we get x is equal to 15 divided by 5, and x is equal to 3. That's as simple as that. We all know this from elementary mathematics. So what does that mean in a algebraic intuition way? So for example, x has a value. X is kind of not 0, right? X is not 0 in this case. And why it is not 0? Because if you see this number, 15 divided by 5, this number here, this one here, right? The denominator, after when you're trying to find the x, the denominator cannot be equal to 0 for the solution to exist. Meaning what? For x to exist, the denominator cannot be 0. For example, if I get something like this, 15 by 0, the x is not defined. This whole thing is not defined. Mathematically, it's not possible, right? So for the x to even have some meaning or some value, the denominator on the other side need to exist, and it cannot be 0, right? That's what it means. In other words, if I have to paraphrase, what I can say is the denominator, this piece here that I'm talking about, right, which I'm circling, this piece here, the denominator in this equation determines if a solution to this whole equation exists or not. That's what we are trying to understand, right? And hence the word determinant. So now you understand where this word determinant is coming from, right? This word is determinant is coming from the fact that if the solution has to be solvable, or if the solution has to exist for this one equation, one unknown, the denominator over here cannot be 0. Okay. That's one. And the other thing is this piece that I've circulated. What is it at the end of the day? At the end of the day, it is just a number. That's it. It's just a number. It can be positive or it can be negative, but it cannot be equal to 0. That's what we are saying here, right? So far with me? Okay, cool. So now let's do one thing. Let's do a small detour. Let's take things on this left hand side over here, right? And let's try to generalize or abstract it. Meaning what? We'll not use the numbers. We'll just use some unknowns to denote these numbers, and just trying to understand where we are going with this. For example, 5x is equal to 15, right? So if I am going to substitute 5x is equal to 15, let's say I'm calling this as a, and x can remain as x, and I'm calling this as y. Over here, I'm just substituting the numbers with some variables or with some letters, right? A is equal to 5, x is equal to x, and y is equal to 15. And I'm going to exactly mimic each step on the left hand side, on the right hand side. So the first step is 5x is equal to 15, right? So what does it mean? Over here, if I have to replace that, I'm going to say that a into x is equal to y. And over here, I'm going to find the value of x, where I'm having a ratio of two numbers. Similarly, I'm going to find x, and the ratio of two numbers is y divided by a, where a is 5. This is what we're getting. The denominator is 5. So what does it mean? X is equal to y by a. So if I have to apply the same concept or the same conclusion that we arrived on the left, what I'm trying to say here on the generalized formula is, for any equation with one unknown and one equation with one unknown over here, if a solution for that equation has to exist, the denominator, which is the a, which is highlighted in red color, it cannot be 0. Okay, so that means the value of the a, right, the value of the a or the value of the denominator determines if the solution to this equation exists or not. And again, the same thing, hence this value or this a is the determinant of this equation, and it is just a number which can be positive or negative, but not 0. Okay, so hang on with me. So I've just tried to simplify this with one equation, so that if you understand it in one dimension. When I say one equation in geometry, it means one dimension. It's just a line. There is no xy axis. It's just a line. Now let's take this and let's extrapolate this concept to a two dimension, where we have an x and y, because matrices are normally in two dimension or more, right? Let's extrapolate that. And you just remember that the denominator cannot be 0. That's all you need to remember here. Okay. Now let's keep going here. Okay. All right. So now again, I have a left and the right. Let's focus on the left thing. Now we are trying to go into a two dimension. And again, the same thing you'll see in my geometric intuition, where I explain the same problem in a one dimension and a two dimension and three dimension, right? Right now we're talking about the algebraic side. So we are going to draw a parallel to that, where we have two equations and we have got two unknowns, which we're talking about in x and y plane, right? So we are going to have an x and y plane kind of thing, x coordinate and y coordinate, right? Something of that sort. So I've just taken two random equations. I'm going to just quickly walk through what we're doing here. Again, it's solving simultaneous equations, which we have done in elementary maths. So there are two equations given by equation 1 and 2. And if I have to solve this, typically what I do is I eliminate one variable. For example, if I want to find x, somehow I need to make y 0 and vice versa. So in the first case, I'm going to make y 0, and for making y 0, I need to just equate the y terms in both the equations. So what I'm doing is I'm multiplying equation 1 by the number 2. So I get equation 3. Now if you see 3 and 2, which is the same equation over here, now equation 1 has been modified to 4x minus 2y is equal to 2. And the equation 2, which is from here, it's the same. Now I can see that if I just simply do an algebraic addition of these two equations, equation 3 and 2, the y will get eliminated, and I can compute the value of the x, which is what this is. So if you see here, I've computed the value of x is equal to 2. And just remember this for the time being, that x is the ratio of two numbers, 14 by 7, and the 7 is highlighted in yellow for a reason. Just hold it for now. Okay, so the value of x is equal to 2 from equation 4. And similarly, if I do the opposite, where I try to eliminate x to get y, then I can get the value of the y, which is I've done pretty much the same, right? I'm trying to equate the terms on x and then do a simple subtraction. X gets eliminated over here and I get a value of the y. And again, before the pre-final step, before I get the value of the y, if you see y is equal to 21 by 7, again 7 is highlighted in yellow, And the reason I told you to just mark this is, interestingly enough, when I'm finding x and y both, the denominator is still the same, and it's going to be true for all your algebraic equations, right? The denominator is still the same. The denominator in equation 4 and equation 5 is the same, and we'll come what is the point I'm trying to make here. Just hold on that thought over here. So the left side is pretty simple, no magic there. Now as we did in the previous problem, right, over here we are going to generalize the left in terms of variables. We are going to remove all the numbers on the left and replace it by variables, okay, which I'm going to use a, b, c, d, and m and n. So basically I've given it to here what matches where, okay. I've just put it here: a is equal to 2, b minus 1, c 3, d 2, m is equal to 1, and n is equal to 12. And the same thing for every step. I'm replacing, I'm having a counterpart on the right side in terms of variables, okay. I'm putting it here. And while we do that, before that, what we do is, since we are trying to go back between system solving linear equations or systems of linear equations and metrics, let's quickly just write this whole thing into matrix format, which will be handy in few minutes from now, okay. So if I write this whole thing in matrix format, I'm going to open up 3 matrices, okay, like this. I'm just going to write the variables. The first one is 2 minus 1, the second one is 3, 2. I'm going to put the x and y here and the 1 and 2 here. That's all I'm going to do, okay. And similarly, since I've written the matrices over here, I'm going to, let's say I'm going to write it over here, for example, or let me write it here. So it's going to be simple 3 matrices, okay. Sorry about my real estate consumption. I'm going to write it simply like this, okay. And I'm going to write it like that, okay. I've written like that, okay, just for a matrix notation, and we'll come to that. So again, continuing our thesis on whatever I'm going to do on the left, the way I've solved this algebraic equation, I'm going to generalize on the right, and for each step I'm going to just replace it by the variables. And if you see, I'm just doing it here where I need to find the value of x and I need to make y 0. So what I'm doing is I'm multiplying this equation by d, and this equation I'm multiplying by b, so that y gets eliminated. The way you see here, I get bd over here, I get bd, and then I can, if I just subtract these 2 equations, y will get eliminated. It will give me a value of the x over here, right? Okay, equation 7. So if you see, again, x is represented as a ratio of 2 numbers, just like how we had it here, 14 by 7 on the left. We over here we have in terms of variables. That's why it looks complicated, but this will make sense in few minutes. So just remember, mark this equation in yellow, equation 7. X is equal to dm minus bn divided by ad minus bc, and we know that this denominator 7 was equal in both the cases, so we are going to have the same functioning here. And I'm going to solve for y. For solving y on the right side, I'm going to make x is equal to 0 by the same logic. And when I come to that particular part where I equate it and I eliminate the value of x to get y, I get equation number 12, where it says y is equal to minus cm plus an divided by ad minus bc. That's your equation 12. And if you see this equation 12 and 7, the denominator is equal to same. That's what you see, which should be the same because that's what you get in the left side. So the denominator is ad minus bc. And like we explained in the earlier problem, the denominator has to exist. It cannot be 0 for the solution to exist, because over here 7 is not equal to 0, and hence we can get the values of x and y. That means even if I generalize, what I'm trying to say is the denominator over here cannot be equal to 0. That's what we are trying to come at, and that's what I've kind of written it here. So what I'm trying to say, for getting the value of x and y, for x and y to exist so that the solution will have a value, the only condition that we need to have is it will exist if and only if the denominator is not equal to 0. I'm just repeating it several times. It's not equal to 0, which in this case is ad minus bc. ad minus bc is not equal to 0. So when you solve a 2 by 2 matrix or a 2-dimensional matrix in an x and y plane, the denominator which is determined by ad minus bc cannot be equal to 0. In a single dimension, it's just one variable over here, a. It cannot be equal to 0. In 2 dimension, it's going to be a set of 4 variables, and in 3 dimension it might be more variables. We'll come to that. So just mark this for now. The denominator AD minus BC cannot be equal to 0. In other words, 7 cannot be equal to 0 over here. Okay, and if I have to rephrase that again, like I repeated in the above example, the denominator, which is AD minus BC, determines if the solution exists among many other things, and hence this particular combination or this denominator for this 2 by 2 matrix or this set of 2 equations and 2 unknowns is called the determinant. The denominator is called the determinant, which is AD minus BC. Okay, so far so good. Okay, now if you see here, I've already expressed this into matrix notation, and you will see here when I'm saying here AD minus BC, it's just a cross multiplication over AD minus BC. So AD minus BC, it's a cross multiplication, and the cross multiplication kind of happens from the top left corner. It has to start from the top left, come at the bottom right, and then the other diagonal. So that's how it is done, right? Because that's what it will match. You cannot do it vice versa. So top left to bottom, and then the other one. So AD minus BC. So basically it's the product of the diagonals starting from the top left to bottom right and the difference of that. That's what it means. So I'm just I'm rewriting the equation, because now we need to get into how do you express determinant of a matrix, right? Now we have some kind of understanding. The same matrices that I've written in the doodle in the matrix notation over here, I've just taken this part right over here and here. I'm rewriting at the bottom here for sake of simplicity. Okay, so the left side I've written as this. There are 3 matrices, one with numbers, one with xy, and one with the right hand side, and I'm calling this thing as the matrix, because you need to remember that the determinant is for a matrix. A matrix has to exist because matrix is kind of the womb. If you remember my matrix intuition of why matrix is which came first, kind of that video, matrix is the mother and determinant is the child. So matrix is the womb and it gives birth to the determinant. So the matrix has to exist, and then only we can find the determinant of a matrix, right? We don't find a matrix of a determinant. We always find a determinant of a matrix. So I've written this equation like this, and the point I'm trying to make is how is determinant expressed, right? Determinant is expressed. Determinant of a matrix is expressed in one of the following ways. Either we can say DETA, which is determinant of matrix A. In this case, this is the matrix we're talking about where we are finding the determinant, or it's represented by a simple triangle, which is called as, I think, delta or a triangle. And in terms of the notation, if you see, the matrix will always, matrix is a rectangular area of numbers or an area of numbers which is enclosed in this kind of brackets, opening and closing square brackets. And determinant is nothing but an area of numbers which will not be in the brackets, but which will be in between 2 simple vertical lines, like a pipe operator. There are 2 lines in red. That's the reason I put in red. So that's how you determinant, that's how you find out when a given set of numbers are given, whether it's a determinant or a matrix. If it's within the opening and closing square braces, it's matrix. If it's just simply put within 2 vertical lines or straight lines, it's a determinant. And the different ways to express are either you can say determinant of A, which means determinant of a matrix A, or you can put a small triangle, and the numbers itself, the area of numbers itself can be represented by 2 vertical lines. So different ways of expressing that it's a determinant. On the right hand side, when you generalize, you put A, B, C, D, the same stuff here. And if this is the given matrix, all this thing means denoting determinants in different fashions. You can write determinant in the bracket A, which means determinant of this matrix. Or you can write A and put 2 straight lines as if you're putting the area of numbers. And this will also mean that you're trying to find out the determinant of a matrix. And the numbers itself can be in 2 simple straight vertical lines, which is highlighted in red, I put. Or you can also say that a triangular, the same stuff. So this is what kind of an algebraic kind of an intuition, where this formula where you have this cross multiplication AD minus BC comes from. Typically textbooks start from this point, that is what is the determinant of a matrix, without giving it an opportunity of where it comes from, how it comes from, all those things. That's why the textbook definition starts. So I thought that if you need to understand what is a bit of logic here, why that is where is it coming from, it is coming from basically the way simultaneous equations are solved, and when you generalize, the denominator cannot be 0, and that particular number determines whether the solution exists or not, and that number can be positive or negative but cannot be 0, and that's the intuition. And I'm just summarizing it here. Square brackets for a 2 by 2 matrix is matrix. The determinant of a matrix, which is written here in between two straight lines, is when it's straight lines, two vertical lines, is a determinant. And whenever you write a 2 by 2 matrix, the simple way to remember, whenever you apply the formula in exam, whenever you have to find the determinant of a matrix, the number, you write the matrix or the determinant in the array format and just do a cross multiplication. But always take the first two products should be the number on the top left and on the bottom right, this diagonal multiplied by this diagonal and the difference of that. That's how it is done. So that kind of sums up kind of an algebraic intuition or an algebraic understanding of a 2 by 2 matrix and determinant. Coming up in the next video is the determinant or determinants for 3 by 3 matrices. There are slightly different and slightly bigger formula, and hence I'm going to put a separate video. Hopefully you guys enjoyed this video and it gave a bit of sense of where things are coming from before you really start solving problems. Stay tuned, more in next video.